Hey guys, so sorry I can't be there at the AI Plumbers Conference in person this weekend. It would have been really nice to come down and see what everybody's doing, but I just can't make it to Berlin at the moment. So instead, I'm going to give my talk remotely, and thank you to the organizing team for letting me do this. So as a company, we at Empergoz do a lot of work with low-level tool chains, and in the last few years, this has been a lot of work with low-level AI tool chains. Something that people keep coming to us and asking is to get PyTorch to work on their novel piece of hardware. And this is fine when people are doing sort of data center class novel hardware, but when things are being done on sort of very low power devices, sort of mobile or edge devices, things get a lot trickier because PyTorch is quite a big beast and there's just far too much overhead to run on embedded class processors or just smaller processors. So today I'm going to set out how we can solve this problem. And I hope you go away with both an impression of how this problem can be solved and also some anticipation for our blog post that we'll be publishing in detail about this later in the year. And just to be very clear as well, because this is a lightning talk, I'm basically going to just describe the solution to doing PyTorch on embedded class devices and the problems that need to be solved, but I'm not going to be providing the solutions to those problems, partially because there's not time and partially because we are going to be doing that in our blog post later in the year. Anyway, so the problem that PyTorch is too big to run on lower power devices is well known, and the PyTorch team over the years have given us several different solutions to sort of doing PyTorch models on smaller devices. And the current way of doing it, the sort of current effective way to make this work is called Executorch. I think this has been the de facto standard for about 2 years now. And it's essentially a runtime for running precompiled PyTorch models. Just a very minimal runtime that can be executed on low power devices, potentially even on embedded class devices, which don't have things like operating systems. And it does this by having just a much smaller operation set, a sort of very simple execution. So just a quick reminder about how all of these tools work, and Executorch is no exception. Sort of conceptually, though, the details of how Executorch works are how Executorch implements all of these things, I suppose, is a little bit different. So all of these AI tools ingest neural networks as graphs. So the nodes in the graph represent operations to be done like convolution, addition, multiplication, and the edges represent the flow of data between these nodes. And we take these graphs, we might do some graph level transformations, things like merging add and multiplies to be add multiply or something. And then we take this graph and we iterate through the graph node by node. And for each of these nodes, we decide where we're going to execute it with the dispatcher. We do that execution, and then we repeat this until we've executed the whole graph. Now, for PyTorch proper, we do this with what's called eager execution, where we just sort of take our graph or our graph. We take our graph and we just walk through the nodes without any looking at the rest of the graph, and just sort of do things in turn. For Executorch, we can't really do that, and we need to make some effort to compile things ahead of time to save time and space. And the workflow for getting Executorch to work within PyTorch is as follows. We take our PyTorch model and export it to one of PyTorch's or to PyTorch's serialized model format. As part of this, we do the very critical step of lowering the extremely large set of possible PyTorch operators down to a much smaller set of atomic operators that Executorch can work with. At the same time as we are compiling our model, we also decide where each of these operations is going to be executed. And this is a little bit different from normal PyTorch, because in normal PyTorch, it's up to the user to decide where their data is at any given point, and where they want operations to be executed. And then essentially, when we have done this, we end up with a serialized PyTorch model, and we can pass this to our Executorch runtime and sort of go over executing it. Now, the process of making this work on a novel piece of hardware is actually quite different to getting things to work in PyTorch, as we described in our presentation earlier in the year. When it comes to getting PyTorch fully to work on a novel piece of hardware, there's a bit of challenge with rewriting the dispatcher in PyTorch to sort of take your operations and do them on your new piece of hardware. But by far the bulk of the work is in finding a way to provide efficient implementations of these sort of thousands of PyTorch, potential PyTorch operators on your hardware and provide good ones, because it's just not feasible to necessarily write these by hand. And when we presented this last time, we spoke about some ways to get at this issue. For Executorch, though, the challenge of getting things to work on new hardware is a little bit different. Because we have a very limited set of edge operations, it is actually feasible for us to go through and basically just provide implementations for these on our embedded class processor and or our embedded class processors accelerators if they have one. But because of the sort of very stripped down nature of Executorch, we end up with a whole bunch of other challenges that we need to meet to get it to work instead. So these are the primary challenges. Of course, we need to be able to make sure that we can compile our Executorch runtime for the hardware that we're working on. Now, if this is a fairly simple piece of hardware, this isn't too bad. If you have something like a RISC-V, a novel RISC-V core, that's absolutely fine. RISC-V core support is fairly good in the sort of GCC and LLVM compilers, and that's not too much work. But if, as occasionally happens, people come to us with extremely novel hardware, then you need a compiler for your hardware as well as everything else, and that is potentially quite a lot of work. Interesting work, but quite a lot of work. Anyway, but separately from this sort of necessary step, we also need to think about some sort of higher level things that we need to do as well. So in terms of the workflow that I just described, one thing we need to do is, if we have them, we need to be able to support hardware specific operations. We might end up with the case where you wish to pull functionality from your hardware in PyTorch that is not supported by normal PyTorch operations. Maybe you have a special digital signal processing thing, which you want to call from PyTorch, and we need a way of taking that and lowering it all the way through the model export process to be executed in Executorch. We need, obviously, to go away and implement the set of Executorch operations on our new piece of hardware. As I've said, if your hardware isn't too novel, that's not necessarily too bad. But if your hardware is novel, that's potentially quite a time-consuming and difficult step to do well. This process of deciding where to execute each operator, that should really, I suppose, be deciding how to execute each operator, is another thing as well. And to do that, we need to potentially write a partitioner and to sort of help decide at compile time where we're going to execute things. And for an embedded class processor, this is not necessarily just a simple, this process of deciding how we execute each operation is not necessarily just a simple thing of, oh, we'll execute it on the CPU, or oh, we'll execute it on the accelerator. Depending on how our embedded class hardware works, we might have to be making decisions about memory management when we do that. We might be having to do that manually. And that's potentially, doing that right, there's potentially quite a lot of work. And when it comes to our Executorch runtime finally executing things, the Executorch runtime as it stands is very, very, very simple. It will literally walk over the graph, it will execute each node in turn, and simply wait for the result to come back. If you want to do complicated things like asynchronous execution or sharing your execution between your cores and your external hardware, or just anything more than that, then that's something you have to write manually as well. And that's actually quite important. If you want your embedded class processor to perform well, this is where the performance gains are. It's not the first thing you have to do, but it's a very important thing. Anyway, this is where these are the problems with Executorch, whose solutions we are going to be detailing later in the year. I hope this has given you a good view of how you can do PyTorch and embedded class processors, and what the type of thing that needs to be done to make that work. You can find our blog later in the year on our website, which is available here. Anyway, thank you guys for listening to this talk. If you want to get in touch, my contact information is here. If you have any questions, thoughts, comments, it would be really well received. Thank you. And again, sorry that I just couldn't be there in person this time.